Ideal gas law. The goal of this video is to determine the ideal gas law by relating all the laws in the previous video to form a single equation. We'll then use the ideal gas law to determine one of the missing variables for a given set of conditions, and finally use the ideal gas law to determine how a system changes under a new set of conditions. While you can also use Charles, Boyle's, Gay-Lussac's, or Avogadro's law individually, I find it is simpler to always start from the ideal gas law ratio to solve for a changing set of conditions. I have waited to show you any such examples until we have first been introduced to the ideal gas law for this reason. If we combine all the relationships from the previous video, you will get PV equals nRT. You can see how increasing temperature increases pressure if everything else is held constant, or how increasing pressure must decrease volume if all else is held constant, and can similarly walk through each of the possible options from the previous video. R is a constant and therefore does not change. If you know 3 of the given variables, you can solve for the other variable. We'll do 2 examples of that now.
Let's look at an example. We have sulfur hexafluoride is a colorless, odorless, very unreactive gas. Calculate the pressure exerted by 1.82 moles of the gas in a steel vessel of volume 5.43 at 69.5 degrees Celsius. We'll start with the ideal gas law. Let's look at what we're trying to solve for. We'll solve for that variable. In general, I prefer to rearrange the equation first and then fill in my numbers. We need to make sure that all of our units are correct. Typically, the easiest way to do that is to look at the units on R, make sure that everything matches up. And always, 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 you'll need to make sure to convert into Kelvin. From here, we simply plug into our calculator to get our answer. Now let's do another example where we will again be solving using the ideal gas law. In this case, we'll be solving for volume. However, we will fill in just like before. Remember to convert to Kelvin. And remember to check that all our other units match up, which we have atmospheres, moles, and Kelvin, so we are fine. We can see that we'll have liters when everything cancels out to get 9.29 liters. Now let's look at how we can use the ideal gas law to solve for a variable when we are changing conditions. For example, what if we have a problem where a balloon is rising in the atmosphere? Temperature and pressure will change as it increases in elevation. Now what will happen to the volume? We can set up a ratio by using the ideal gas law. Since we know that R is a constant, let's put all the variables on one side. If we can do this for one set of conditions, we can do it for another set of conditions. Now, since R is the same for any given set of conditions, that means that we can set the 2 equations equal to each other. From here, we can solve any ideal gas problem where some of the variables are changing. Let's take the example that I have here and finish the problem. Here I have listed out the variables in a slightly easier to see form. I suggest doing this if you often make mistakes when filling into equations. Let's take note of what is changing and what is staying the same. P, V, and T are all changing, while we are not changing the number of moles. Therefore, N is the same on both sides and can be canceled out. From here, we can fill into the equation and solve for the unknown. In this case, V2. We must always convert into Kelvin. And notice that when I made my list, I put the plus 273 there as well to make sure that I didn't forget. From here, we solve for V2 to get 1.33 liters. We must always check our sig figs. And in this case, the question was really written for 2 sig figs since each of the numbers given have 2 significant figures. So we will have 1.3 liters. If you're saying, what about the 70 and the 60 degrees Celsius? Don't forget that you added it to 273. And when we add to 273, you keep to the number of places, not the number of significant figures, therefore also leaving us with 2. Let's do another example. It's a bit more relevant. If you were engineering a light bulb, for example, you'd want to know how much pressure it would be created by the gas inside being heated. If the glass can't handle that pressure, it's going to need to be altered to keep the light bulb from bursting. We'll start from the same ratio. We'll again decide what's staying the same and what's changing. Since it's a glass light bulb, volume can't be changing. Since it's the same on both sides, it cancels. And there is no gas coming in or leaving. And so the number of moles are constant as well. This leaves us with that. From here, we can solve for the variable that we need and fill in our numbers. Being very careful, fill in Kelvin. Leaving us with 1.48 ATM. One last example, this one also very similar to the first one. We have a bubble rising from the bottom of the lake with a certain temperature and pressure, rising to the surface with a new temperature and pressure. We want to find the volume of the bubble at the surface if we know that its initial volume was 2.1 mils. We can again list everything out. Whether you want to do that is up to you. I find it helps to prevent mistakes when filling in lots of numbers. Notice for my temperatures, I right away add in my 273. Of course, you're also welcome to just add that number in. I leave it like this for the sake of showing you what I did. Now, notice I left my V1 as 2.1 mils. And you may be saying, well, you have to convert that into liters because I know that R has a liters in it. That would be a really good thought. But the nice thing about using these ratios is that because it's the same on both sides, you can be a little lazy with your units. This is, however, not true for temperature. And let's think about why that is. For pressure, volume, and I suppose even number of moles as compared to number of atoms, if you are converting between liters and milliliters, let's say for volume, you would be multiplying or dividing by 1,000 here, and same thing over here. So because it's multiplication or division, depending on how you do that conversion, it cancels out. Whatever I fill into volume here is going to come out in my volume here. That's not true with temperature because of that addition. Because it's a Kelvin to Celsius, it's addition, and that works differently mathematically. So you always have to use Kelvin, but pressure and volume, you can be a little lazy with your units. So let's solve for V2 and fill in all of our numbers. From here, we type into our calculator, round to the correct number of sig figs, and we have 14 mils. Because we had mils here, we're going to get mils here. We can see that our atmospheres cancel, our kelvins cancel, and it leaves us with milliliters. We have now learned how to relate many variables of an ideal gas together into one equation called the ideal gas law. You can use this to determine an unknown variable at a given set of conditions, or can use it to see how changing conditions will affect one of the variables.